Chapter 7. Data Science and AI. 7.1 Role of Data in AI. The emergence of blockchain technology has revolutionized various fields, with artificial intelligence, AI, being one of the most significant beneficiaries. Data plays a critical role in the functioning of AI systems, serving as the fundamental building block from which algorithms learn and make decisions. In essence, data acts as the fuel for AI, allowing machines to recognize patterns, make predictions, and improve performance over time through continuous learning. AI relies on high-quality data to operate effectively. For machine learning models, the adage, garbage in, garbage out, succinctly captures the importance of good data. The data used for training these models need to be accurate, comprehensive, and representative of the real-world environment in which the AI will function. This implies that data collection methods must ensure diversity and volume, mitigating biases that could skew the model's outputs. In this regard, blockchain can offer a transparent and immutable record of data provenance, enhancing the reliability of the data used in AI applications. Processing vast amounts of data is a core requirement for AI systems. The computational power required to analyze large datasets can be immense, especially when working with complex neural networks and deep learning techniques. Blockchain technology, with its decentralized architecture, has the potential to distribute the processing load across multiple nodes, thereby increasing efficiency and reducing bottlenecks associated with centralized data processing systems. This distributed approach can facilitate the handling of large-scale AI tasks that require considerable computational resources. The volume of data required for AI also signifies a need for efficient storage solutions. Blockchain technology offers a decentralized storage framework, which has the advantage of reducing the risk of data loss due to system failures or cyberattacks. This decentralized storage system can be instrumental in providing AI systems with access to vast datasets without the central point of failure that traditional cloud storage solutions may present. Furthermore, blockchain's inherent security protocols can protect sensitive data that AI systems might analyze, such as personal information or proprietary business data. Data integrity is paramount in AI. The decisions that AI algorithms make can be only as trustworthy as the data they are trained on. Blockchain's capability to create tamper-evident records ensures that once data is entered, it cannot be altered without leaving a trace. This level of data integrity is crucial, especially in fields where AI decision-making has significant consequences, such as in healthcare, finance, or autonomous vehicles. Trusting AI's decisions requires an unwavering confidence in the veracity of its underlying data. Interoperability is another aspect where the convergence of blockchain and AI shows promise. Different AI systems may need to collaborate, exchange information, and learn from each other to solve complex problems. Blockchain can facilitate secure and seamless data exchange between disparate AI systems, maintaining the integrity and privacy of the data. The standardization of data formats and protocols on a blockchain can enable various AI systems to interact and learn from a shared pool of data, potentially leading to more robust and intelligent AI solutions. Ensuring privacy in the use of AI is a growing concern, particularly with regulations such as GDPR emphasizing the protection of individual data. Personalized AI experiences often require access to sensitive personal data, yet there is a need to safeguard this data against misuse. Blockchain can provide a framework for privacy-preserving AI systems where users have control over their data and can grant selective permissions for its use. Smart contracts on blockchain platforms can automate the execution of these permissions, ensuring compliance with user consent and regulatory requirements. In addition to improving existing AI practices, blockchain can also catalyze the creation of new AI models. For instance, blockchain can enable a novel AI concept known as decentralized autonomous organizations, DAOs. These are AI-driven organizations that operate autonomously based on coded rules on a blockchain. DAOs require constant interaction with external data and rely on smart contracts to execute decisions. The role of data in these organizations is critical, as it needs to be current, reliable, and verifiable to ensure the correct functioning of the DAO. In the context of AI research and development, data sharing can be a contentious issue due to competition and intellectual property concerns. Blockchain technology introduces a means to create data marketplaces, allowing entities to buy, sell, or share data in a secure, transparent, and auditable manner. These marketplaces can democratize access to valuable datasets, accelerating AI innovation, while also providing a mechanism for compensating data providers. Furthermore, as AI continues to evolve, there is an increasing need for more sophisticated data governance models. Blockchain's decentralized control structure offers a novel approach to data governance, negating the need for a central authority and empowering stakeholders to have a say in data-related decisions. This decentralized form of governance can ensure a fair, transparent, and accountable use of data within AI systems, fostering trust among users and stakeholders involved. The role of data in AI cannot be overstated, and blockchain technology presents new paradigms for data handling that could address many of the challenges faced by the AI sector. As AI systems become more integrated into daily life and critical industries, the synergies between blockchain and AI will likely become a focal point for innovation. This collaboration can enhance the capabilities of AI while ensuring that the data it relies on is handled with the utmost integrity, security, and respect for privacy. Through blockchain, we have the potential to foster AI systems that are not only intelligent, but also ethical, accountable, and transparent. 7.2 Data collection and management. The amalgamation of blockchain technology with data science and artificial intelligence, AI, is pivotal in transforming how data is collected, verified, and managed. As digital data becomes more integral to decision-making processes in various sectors, the mechanisms for handling this data must not only ensure integrity, but also enhance security and accessibility. Blockchain has emerged as a technology well-suited to address these needs due to its intrinsic characteristics, which include decentralization, immutability, and transparency. Blockchain's decentralized nature allows for data to be collected from multiple sources without the need for a central authority. This feature drastically reduces the risks of single points of failure and enhances the resilience of the data management system. Data is stored across a network of computers, known as nodes, making it exceedingly difficult for any malicious actor to corrupt or manipulate the data. In addition, every node has a copy of the entire database, which is continuously updated and verified through a consensus mechanism, ensuring that each data entry is accurate and legitimate. The immutability of blockchain is another critical attribute for data management. Once a piece of data is recorded on a blockchain, it cannot be altered retrospectively. This ensures that historical data remains unchanged, providing a reliable and auditable trail of information. Data scientists and AI systems can leverage this property to analyze data over time and derive insights without the concern that the baseline information may have been tampered with. The immutable record serves as a source of truth that can be integral in sectors where data integrity is paramount, such as finance, healthcare, and legal affairs. Transparency within a blockchain network facilitates a level of openness that is often unattainable in conventional databases. While maintaining the confidentiality of the parties involved, blockchain allows stakeholders to view and verify recorded transactions. This aspect is very important for building trust among users and is vital for collaborative data management efforts where multiple entities need assurance of data veracity. For instance, in supply chain management, participants can trace the life cycle of products transparently, enabling responsible sourcing and reducing fraud. Another cornerstone of data management on the blockchain is smart contracts. These are self-executing contracts with the agreement terms directly written into lines of code. The code and the agreements contained therein exist across the distributed blockchain network. Smart contracts can automate data collection processes, ensuring that whenever predefined conditions are met, data is captured and recorded. This system significantly reduces human error in data entry and provides a streamlined process for collecting data in real time, further improving the accuracy of datasets used by AI algorithms for various applications. Interoperability across different blockchain networks and traditional databases is also a focal point in data management. Technical standards are being developed to facilitate seamless data exchange and communication between disparate systems. This interoperability is essential for creating a cohesive data ecosystem, where information from various sources can be integrated and analyzed effectively. The ability of different AI systems to access and interpret data across platforms can lead to more comprehensive insights and innovative solutions to complex problems. The aspect of user control over data is revolutionized by blockchain. Individuals can have greater control over their personal data and can selectively grant access permissions via the blockchain. This can enable users to benefit from personalized AI services while retaining their privacy. Data collection methods that respect user sovereignty are increasingly important in an era where data privacy concerns are at the forefront of public discourse. The use of blockchain also addresses the challenges of data provenance, meaning the origin and history of data. Establishing provenance is critical for validation and is essential in scenarios where the source of data impacts its reliability. Through timestamping and securely linking data records, blockchain provides a framework for establishing provenance that is not easily repudiated, which is particularly useful for data science applications that often require the use of large, historically relevant datasets. From the standpoint of data storage, blockchain-based systems offer innovative solutions. By integrating blockchain with decentralized file storage systems, data can be stored across a network in a fragmented and encrypted form, enhancing data security. As with the blockchain's ledger, encryption and off-chain storage contribute to a secure data environment essential for sensitive data that AI systems might process, such as personal health records. Funding and incentivization mechanisms for maintaining data integrity and quality can also be integrated into a blockchain-based data management system. By using tokens or cryptocurrency, participants can be rewarded for contributing quality data and penalized for dishonest behavior. This could create a self-sustaining ecosystem where the accuracy and comprehensiveness of data improve over time, directly benefiting AI systems that rely on high-quality data for machine learning and predictive analytics. Lastly, it's important to consider the challenges associated with integrating blockchain into data management practices. These challenges include the need for significant computational resources, potential scalability issues as the volume of data grows, and the necessity for a robust governance framework to manage the network effectively. Even though blockchain offers numerous benefits, it is not a panacea for all data management concerns. However, the ongoing development of the technology and its integration with advances in data science and AI indicates a promising direction for its evolution. As a result, blockchain technology is poised to become an essential foundation for future data management systems that will significantly empower data science and AI capabilities. The intersection of these technologies has opened new avenues in data handling that could potentially disrupt traditional systems, leading to more robust, trustworthy, and intelligent data usage that informs decisions across all sectors of society. 7.3 Data Pre-processing Techniques. Data pre-processing is an essential step in both data science and artificial intelligence (AI) when implementing blockchain technology. Within this domain, quality data, rather than sheer volume, reigns supreme. Thus, pre-processing involves transforming raw data into a format that can be easily and effectively analyzed for insights and decision-making. This chapter covers a spectrum of techniques employed for data pre-processing and the rationale behind their significance. One fundamental technique in data pre-processing is data cleaning. Despite blockchain's reputation for being a secure and immutable ledger, the data that enters the chain can still contain inaccuracies, inconsistencies, or missing values, particularly if derived from external sources. The data cleaning process aims to rectify these flaws by filling in missing values, smoothing noisy data, identifying and removing outliers, and resolving inconsistencies. This is often achieved through algorithms and data imputation methods that enable the restoration of data integrity. Depending on the context, various strategies may be employed, such as mean imputation, hot deck imputation, or using regression models to predict and replace missing or erroneous values. Data transformation encompasses various procedures that modify the data's range and central tendencies to better expose the underlying data distributions and relationships. Techniques such as normalization and standardization are common. Normalization adjusts the data to fall within a smaller common range, such as -1 to 1 or 0 to 1, which is particularly beneficial when dealing with parameters that exhibit widely differing scales. Standardization, on the other hand, reshapes the data to have a mean of 0 and a standard deviation of 1, aligning with the properties of a standard normal distribution. Both techniques are critical when implementing machine learning algorithms, which may perform poorly if input variables do not conform to specific scales. Another major preprocessing technique is data reduction, which aims to decrease the volume but produce the same or similar analytical results. High-dimensional data, common in blockchain contexts due to the extensive logging of information, can lead to complexities and longer processing times, known as the curse of dimensionality. Data reduction techniques, such as principal component analysis (PCA), help in reducing the feature space by identifying the most informative features. Other methods include selecting k-best features, various forms of binning, and aggregation operations. These not only make computation more efficient, but also may enhance the performance of predictive models by eliminating noise and redundancy from the data. Data discretization is a preprocessing step that transforms continuous data into discrete bins or intervals, which can be beneficial for certain types of analysis or algorithms. For instance, age as a continuous variable might be categorized into young, middle-aged, and elderly. Discretization aids in simplifying complex data structures, making certain types of analysis more tractable and sometimes more meaningful when specific categories are of interest over continuous measures. Techniques applied for discretization often depend on the underlying distribution of data and the analytical objectives, but can include equal width binning, equal frequency binning, and entropy-based binning. Attribute construction, another preprocessing step, involves the creation of new attributes or features from the existing set of attributes, which can potentially help in improving the accuracy of predictive models. This is particularly important in blockchain datasets, where attributes might be cryptographically hashed or otherwise not immediately indicative of patterns or trends. Techniques such as attribute creation allow for deriving new, insightful features from raw blockchain data, making it more amenable to data mining techniques. For example, from timestamp information, one might derive attributes such as day of the week, time of day, or seasonal trends that could provide additional context not captured by the original attributes. Data integration is a complex preprocessing task that involves merging data from multiple sources. In a blockchain context, this might mean integrating off-chain data with on-chain data, presenting unique challenges given the disparate structures and formats. Data must be consolidated in such a way that maintains the integrity and consistency of the datasets. Common techniques for data integration include the use of data warehouses, where data from different sources is transformed into a unified format, cleaned and stored for direct queries and analysis. Data encoding is critical when handling categorical data that algorithms cannot interpret in raw form. Methods like one-hot encoding, label encoding, or binary encoding convert category labels into numerical values. This ensures compatibility with machine learning models that require numerical input. Encoding must be carefully planned, as inappropriate encoding can introduce an unwanted order into the data or exponentially increase the feature space, introducing new challenges. Anomaly detection in preprocessing is vital in ensuring the quality of data before it is used for training AI models. Anomalies in data can represent data entry errors, fraudulent activity, or other significant but rare events that could alter the model's understanding of the normal patterns. Techniques like statistical outlier detection, proximity-based methods, and clustering are used to identify and address such anomalies, particularly in a blockchain environment where security and reliability are paramount. Sampling is a technique used to select a subset of data from a larger dataset to reduce the size of the data that needs to be analyzed. In blockchain, this can be incredibly useful due to the large amount of data that accumulates over time. The challenge lies in achieving a representative sample that reflects the entire dataset's characteristics. Simple random sampling, stratified sampling, and cluster sampling are a few of the methods that can be employed to ensure that the subset of data is a proper reflection of the whole without the computational overhead of dealing with the entire dataset. Finally, feature engineering is an artistic yet systematic approach to data preprocessing that involves selecting those input variables that are most relevant to the task. In blockchain datasets, finding the appropriate features is crucial since they could include transaction volumes, timings, the diversity of interacting wallets, smart contract functions executed, and more. Feature engineering is an iterative process requiring domain knowledge and data understanding to identify what creates a strong signal for the predictive models. Performed diligently, these data preprocessing techniques enable the development of robust AI systems that can provide meaningful insights into blockchain data. By cleaning and preparing data methodically, these systems can deliver dependable predictive analytics, ensuring the utility of blockchain technology across various domains. The success of AI and data science projects in the blockchain realm hinges significantly on the proper execution of these preprocessing steps. 7.4. Big Data and AI. The integration of big data with AI has marked a turning point in the functional deployment and enhancement of blockchain technologies. Big data refers to the massive volume of structured and unstructured data that inundates businesses on a daily basis. However, the value is not just in the quantity, but in the processing and utilization of this data using artificial intelligence, AI. AI is a broad set of algorithms and technologies that enable computers to simulate human intelligence, including learning, reasoning, and self-correction. The symbiosis between big data and AI within the blockchain realm has significant implications for the efficiency, security, and scalability of blockchain networks. One of the critical contributions of big data to blockchain is the optimization of consensus mechanisms. Blockchain consensus mechanisms such as proof of work (POW) and proof of stake (POS) rely on participants' nodes in the network to validate transactions and create new blocks in the chain. By applying AI-driven data analysis to understand patterns in transaction data, blockchain networks can evolve to predict fraudulent behavior and verify transactions more efficiently. AI can assist in analyzing past transactions and social network dynamics among participants, which helps in identifying trustworthy nodes and potentially reducing the number of nodes required for consensus, thereby saving computational power and time. Moreover, AI algorithms are adept at managing the integrity of the blockchain. As the data within a blockchain grows, it could become increasingly challenging to maintain and audit. AI can facilitate the continuous monitoring of the blockchain, quickly identifying anomalies that could indicate data tampering or security breaches. Machine learning models, trained on historical blockchain data, can recognize when the network behaves in unexpected ways, allowing for immediate responses to potential threats. This results in a more secure and robust ecosystem, vital for industries that rely on the incorruptibility of data, such as finance and healthcare. In addition, AI can significantly amplify the smart contract functionality on blockchain networks. Smart contracts are self-executing contracts with the terms of the agreement directly written into code. By employing AI, these contracts can become more intelligent and adaptable. For instance, AI systems can use external big data sources to inform smart contracts and automate complex decision-making processes based on real-time data. This might include adjusting the terms of an insurance payout based on fluctuating market conditions or integrating supply chain data to automatically manage inventory levels. Another advantage of using AI with big data in blockchain networks is the enhancement of scalability. Blockchain networks traditionally face challenges in scaling due to their decentralized nature and the vast amounts of data that must be processed with each transaction. AI models can predict peaks in transaction volume and dynamically allocate resources to handle these increases efficiently. By streamlining data processing and implementing AI-driven data management protocols, blockchain can better support growing numbers of users in increasingly large datasets without compromising speed or security. The synergistic relationship between big data and AI also extends to the personalization of services. Blockchain networks can leverage AI to analyze big data from user interactions, enabling personalized experiences while maintaining the individual's privacy. By doing so, AI can help customize the user interface and suggest services based on user behavior patterns without exposing sensitive data, because the underlying blockchain architecture ensures data remains secure and anonymized. Furthermore, AI can enhance the data analytics features of blockchain by providing advanced predictive models. By drawing on vast datasets, AI can forecast market trends, user behavior, and potential system failures before they occur. These predictive models can aid blockchain users in making informed decisions, reducing risk, and identifying opportunities. For instance, in the context of financial services, AI-enhanced blockchains could predict asset price movements more accurately and suggest optimal times for transactions. While leveraging big data with AI presents numerous opportunities for blockchain networks, it is not without challenges. The complexity of integrating these technologies requires sophisticated algorithms and significant processing power. Additionally, data privacy concerns are inherent when dealing with large datasets. Ensuring that AI systems comply with regulations such as the General Data Protection Regulation, GDPR, while operating on a blockchain is a complex task that involves a thorough understanding of both technologies. Efficient data storage also becomes a critical aspect of combining big data with AI in blockchain systems. Traditional blockchains store every transaction on every node, leading to redundancy and massive data requirements. With big data involved, this approach becomes unsustainable. Consequently, there has been a shift towards more innovative storage solutions, such as off-chain storage sidechains and data pruning techniques, which can help manage the data load more effectively without compromising the decentralized aspects of blockchain technology. The convergence of AI with big data in blockchain creates a fertile ground for innovation across industries. In the context of supply chain management, AI-driven analysis of big data can enable real-time tracking of goods and automate supply chain processes using blockchain's distributed ledger. In the energy sector, AI can optimize distribution in a blockchain-managed smart grid by analyzing consumption patterns. For healthcare, encrypted patient records on the blockchain can be analyzed by AI to provide personalized treatment recommendations while preserving patient privacy. Lastly, the union of big data and AI with blockchain results in a transformative shift in how data-driven decisions are made. The combination of blockchain's immutable record-keeping with AI's advanced computational power and big data analytics leads to more robust forecasting models, smarter contracts, efficient consensus mechanisms, enhanced security, and overall better decision-making. As blockchain technology continues to evolve, the integration with big data and AI stands as a cornerstone of digital transformation in various sectors. Careful consideration must be given to the ethical and practical implications of such integration, but the potential benefits are significant and likely to shape the future of technology. 7.5 Data Visualization in AI. Data visualization is an essential aspect of data science and artificial intelligence, AI. It refers to the techniques used to communicate data or information by encoding it as visual objects contained in graphics. The purpose of data visualization in AI is not only to make analysis results accessible and understandable to humans, but also to provide insights that may not be immediately apparent from raw data. By using graphical representations, complex data can be presented in a more comprehensive and less abstract way, making it easier for stakeholders to interpret and make informed decisions. Visual representations created by AI systems can range from simple bar charts and line graphs to complex multidimensional plots and interactive dashboards. The choice of the right visualization depends on the nature of the data, the message or insight that needs to be conveyed, and the audience's experience with data interpretation. An effective visualization should be self-explanatory, revealing the underlying patterns, trends, and correlations in the data without overwhelming the viewer with too much detail or jargon. In AI, data visualization is not just an output, it's also a diagnostic tool. Throughout the machine learning lifecycle, visualizations can help data scientists and researchers identify inconsistencies in data, detect outliers, and verify assumptions used in their models. For example, they might use a scatter plot to identify relationships between variables or a heat map to show the distribution of values across different dimensions. This aids in feature selection, algorithm design, and the tuning of model parameters. Moreover, in the training phase of machine learning models, visualizations are crucial for monitoring performance metrics such as accuracy, precision, recall, and the receiver operating characteristic, ROC curve. These visual tools allow AI practitioners to compare different models and techniques on a common ground, leading to more objective assessments of their efficiency and suitability for the problem at hand. Visualization in this stage also helps in understanding how changes in the algorithm or data affect the learning process. As AI systems are increasingly used for predictive analytics, data visualization becomes imperative in communicating predictions and their certainty to end users. By representing predictive results and confidence intervals visually, users can quickly grasp where predictions are reliable and where they may need to be taken with caution. This aspect is particularly important in sectors like finance or healthcare, where decisions based on AI predictions can have significant consequences. The integration of data visualization in AI also extends to the interpretation of complex models, such as those in deep learning. Techniques like dimensionality reduction or activation atlases can be used to represent high-dimensional data or a neural network's internal state with a two-dimensional image, enabling a better understanding of how these models process and classify data. This approach can also help in detecting biases in the models or shed light on areas of the input space that cause uncertainty. Interactive data visualization has transformed the landscape of AI insights. It allows users to engage with AI systems by exploring data through interfaces that respond to their actions. Users can zoom in on specific data points, filter categories, or switch views to see different aspects of the data. This interactivity not only enhances the user experience, but also allows for a deeper, more personalized analysis, which can be essential when dealing with multifaceted and high-volume data. Data visualization is also at the heart of the democratization of AI. Effective visualizations can bridge the gap between complex AI models and users with limited technical expertise, enabling broader access and understanding of AI insights. Developers can build user interfaces that represent AI findings in a way that can be easily interpreted by non-experts, thereby empowering more people to make use of AI in their decision-making processes. Ethical considerations are also reflected in the way AI visualizations are presented. It is crucial to ensure that visualizations do not mislead or convey biases inherent in the data or the model. Designing clear, unbiased, and objective visualizations requires careful consideration of color schemes, scale, and context to avoid misinterpretation. The responsible use of visualizations helps maintain trust in AI systems and the organizations that deploy them. As AI systems and technologies continue to evolve, so too will the methodologies and tools for data visualization. Advances in virtual reality, VR, and augmented reality, AR, herald a future where data visualization could involve immersive experiences, allowing users to walk through data in three-dimensional space. These developments could open up new and innovative ways to visualize and interact with complex datasets, ultimately enhancing our ability to derive insights from AI systems. Lastly, to fully exploit the potential of data visualization in AI, continuous learning and improvement are necessary. Practitioners must keep pace with the latest tools, techniques, and best practices. Organizations should invest in training and resources to enable their workforce to create meaningful visualizations. As visualization tools become more sophisticated and integrated with AI and machine learning platforms, the synergy between human intuition and machine intelligence will drive better understanding, innovation, and decision-making across various fields and industries. 7.6 Data privacy and security. In the context of blockchain technology, data privacy and security are of paramount importance. Data privacy refers to the right of individuals to control information about themselves and decides how and to what extent this information is communicated to others. In contrast, data security involves the processes and measures implemented to prevent unauthorized access, use, disclosure, disruption, modification, inspection, recording, or destruction of information. Blockchain technology offers a robust framework for enhancing data privacy and security through its innate characteristics, which can have far-reaching implications for the storage, processing, and dissemination of personal and sensitive data. Blockchain's structural design integrates mechanisms that inherently strengthen data security. First and foremost, blockchain relies on decentralized data storage solutions, meaning that instead of data being stored in a single central repository, it is distributed across a network of nodes. This distribution significantly reduces the risk of central points of failure, which in centralized systems are targets for attacks that could compromise the whole dataset. Furthermore, duplication of the blockchain ledger across nodes ensures that even if one or several nodes are compromised, the integrity of the overall system remains intact, as the consensus mechanism would reject the altered versions existing on the compromised nodes. Encryption is another inherent feature of blockchain that amplifies data privacy. Each transaction on the blockchain is encrypted, creating a unique cryptographic signature known as a hash. This encryption ensures that transaction details are only accessible to parties who have the requisite permissions, typically managed through the use of public and private keys. The public key is shared and can be viewed by anyone on the network, while the private key is kept secret, owned and used by the individual to whom the data belongs. Without access to the private key, deciphering the encrypted information contained within the blockchain becomes exceedingly difficult, thus preserving data privacy. Blockchain technology applies the concept of immutability, making it virtually impossible to alter recorded data without alerting the entire network. Once data has been recorded on the blockchain, changing it retroactively would require an immense amount of computing power to override the entire network consensus. This characteristic significantly enhances the system's resistance to fraud and unauthorized data manipulation, ensuring that historical data remains unaltered and audit trails are maintained throughout the data lifecycle. It is important to note here that while data on the blockchain is immutable, it is still crucial to ensure the accuracy of data before it is entered, as inaccuracies perpetuated on the blockchain are equally immutable. Smart contracts are self-executing contractual agreements integrated into blockchain protocols. They are coded to automatically carry out the terms of an agreement without needing third-party enforcement. Smart contracts increase data privacy by limiting human interaction with the data, consequently reducing the chances of interference, bias, or error. The terms of smart contracts are written directly onto the blockchain and executed when predetermined conditions are met, ensuring data is manipulated strictly according to the embedded contractual terms. However, the immutable nature of smart contracts also implies that code-related vulnerabilities could permanently affect data privacy and security, if not thoroughly tested and audited before deployment. The integration of blockchain technology and advanced privacy-preserving techniques, such as zero-knowledge proofs, offers even more stringent data protection. Zero-knowledge proofs enable one party to prove to another party that a statement is true without conveying any information beyond the validity of the statement itself. This unique property allows for authentication and verification processes within the blockchain without exposing underlying private information. As a result, sensitive personal data can remain hidden while still enabling necessary interactions and transactions across the network. Decentralized identifiers, DIDs, represent a significant advancement in data privacy enabled by blockchain. DIDs are fully under the control of the individual they represent and are not tied to any centralized registry, authority, or intermediary. Such identifiers are used to establish a digital identity that can be authenticated independently, allowing individuals to confirm their identity in digital interactions while retaining control over how much personal information is shared. Blockchain's role in supporting DIDs is fundamental. It provides the infrastructure that ensures the security, portability, and verifiability of these digital identities without reliance on any central authority. The interplay between blockchain and artificial intelligence, AI, potentially strengthens data security practices further. AI algorithms can be employed to detect and respond to anomalies in blockchain networks, effectively identifying and mitigating security threats in real time. AI can harness vast amounts of data with speed and efficiency that are not typically achievable through human efforts alone. By analyzing patterns of transactions and events on the blockchain, AI systems can recognize activities that deviate from the norm and flag them for review, adding an advanced layer of security monitoring that adapts and evolves in response to new threats. However, it is important to address the challenges and limitations that blockchain technology faces in terms of data privacy and security. Despite blockchain's capacity for enhancing data security, complete anonymity is not guaranteed, especially within public blockchains. The persistent storage of data on these public ledgers, while providing transparency, can also potentially expose the information to unauthorized scrutiny. Moreover, there are complications around the right to be forgotten, a legal concept that allows individuals to have their personal data removed from certain situations. The immutable nature of blockchain conflicts with this right, as data cannot be erased once it has been added to the chain. Therefore, careful considerations and legal frameworks must be established to balance individual privacy rights with the benefits of blockchain. Lastly, the adoption of blockchain technology in privacy and security efforts requires sophisticated knowledge and understanding. Users and organizations need to be aware of the responsibilities and competencies required to maintain private keys and manage smart contracts securely. There is a non-trivial learning curve associated with the implementation and continued maintenance of blockchain infrastructure. Additionally, standards and regulations surrounding blockchain technology are still being developed and implemented. Entities utilizing blockchain must stay informed and compliant with changing legal and ethical requirements. Skilled personnel, continuous training, and a proactive approach to regulation are essential components for harnessing the full potential of blockchain in the realm of data privacy and security. In the pursuit of robust data privacy and security, blockchain technology presents a compelling toolset. With its decentralized architecture, encryption methods, immutability, smart contracts, and advancements in privacy-preserving methods like zero-knowledge proofs and DIDs, blockchain can significantly enhance the security landscape. However, challenges remain in aligning its capabilities with existing legal frameworks and ensuring that users have the necessary expertise to leverage its potential effectively. As both the technology and the landscape evolve, the ongoing dialogue and development efforts will determine how its integration into privacy and security infrastructures will be optimized. 7.7 AI in data analysis. The application of artificial intelligence, AI, in data analysis within the blockchain realm is revolutionizing how we interpret vast amounts of data. Blockchain technology creates a high-integrity dataset due to its immutable and distributed nature. AI algorithms benefit from such high-quality data, which improves their ability to uncover insights that might otherwise remain hidden in noise and complexity. AI in data analysis can manage, model, and predict trends from the data generated by blockchain systems. This is especially useful for understanding transaction patterns, detecting fraudulent activities, and making informed decisions based on blockchain data. AI-driven data analysis tools can process and analyze blockchain data much more quickly than manual analysis methods. These tools are equipped with machine learning algorithms that can learn from data without being explicitly programmed to perform specific tasks. A prime use case is the identification of anomalies in transaction patterns that could indicate fraudulent activities. Machine learning models can be trained using historical blockchain transaction data to recognize normal behavior and flag transactions that deviate from established patterns. This process is both efficient and continually improving, as models self-adjust when exposed to new data. The incorporation of AI in blockchain data analysis adds an advanced layer of decision-making capability. Predictive analytics is one domain within AI where this is particularly impactful. Predictive models can analyze historical and current blockchain transaction data to forecast future trends. By doing so, businesses can make proactive adjustments to their strategies based on these insights. For example, cryptocurrency traders could use predictive models to gauge market sentiment and adjust their trading strategies accordingly. Predictive analytics also holds value for supply chain management on blockchain, predicting delays, demand surges, and inventory shortages based on historical data. Natural language processing, NLP, a branch of AI, offers notable advantages in interpreting the textual data associated with blockchain transactions. User comments, contract terms, and transaction descriptions inscribed on the blockchain contain rich information that quantitative analysis alone may overlook. NLP can extract meaningful insights from this data by, for instance, analyzing sentiment, categorizing content, and detecting relationships between contracts and transactions. NLP thus improves the qualitative analysis of blockchain data, which, when combined with quantitative models, leads to a more holistic understanding of transactions. Moreover, AI facilitates the clustering and classification of blockchain data, thus enhancing pattern recognition. Clustering algorithms help in segmenting data into distinct groups with similar characteristics, which is imperative for understanding the structure and evolutions of blockchain ecosystems. For example, in the crypto space, clustering can help identify wallets that are commonly used together, which may indicate a network of users. Similarly, classification algorithms can categorize different types of transactions or contracts, aiding in the smooth operation and monitoring of blockchain systems. Deep learning, a subset of machine learning characterized by neural networks with multiple layers, shows much promise in blockchain data analysis. It is particularly adept at handling the nonlinear and complex relationships inherent in large-scale blockchain datasets. Deep learning models are capable of feature extraction, transforming raw data into a form where hidden patterns become more apparent. Fraud detection systems based on deep learning are becoming increasingly robust, drawing on the pattern recognition capabilities of these models to identify subtle and sophisticated fraudulent schemes on the blockchain. The synergies between AI and blockchain also extend to improving blockchain networks' performance. AI can inform consensus mechanisms within blockchains, helping to optimize the process of validating transactions and creating new blocks. This optimization can contribute to faster transaction times and lower energy consumption, which are critical aspects of blockchain scalability and sustainability. Additionally, AI models could provide recommendations for network configuration and optimization, ensuring the blockchain operates at peak efficiency. Data visualization is another area where AI contributes significantly to blockchain data analysis. Complex blockchain networks generate intricate data patterns that are challenging to decipher without sophisticated visualization tools. AI-driven data visualization tools can transform raw blockchain data into interactive graphs and maps, making it easier to identify trends and relationships at a glance. These visual representations enable stakeholders to quickly grasp the implications of the data, which is crucial for decision-making and strategy formulation. Moreover, AI helps in improving the security of blockchain data analysis processes. With the blockchain's immutable ledger, every transaction and its associated metadata are vulnerable to analysis, which raises privacy concerns. AI can assist in the development of mechanisms such as differential privacy and homomorphic encryption, which allow for the analysis of encrypted data without exposing individual data points. This provides a layer of security that is vital for maintaining the privacy of participants in a blockchain network while still allowing for robust data analysis. Finally, the use of AI in blockchain data analysis poses some challenges that require careful consideration. The quality and the integrity of the data used in training AI models directly affect the outcomes and insights they produce. Since blockchain's ledger is immutable, it's crucial that the data initially recorded is accurate, as mistakes become part of the permanent record. Additionally, the explainability of AI decisions, which is often referred to as the black box problem, remains a significant concern. It is necessary to develop AI systems that provide transparent and understandable decision paths, especially when these decisions have far-reaching economic or legal implications. In summary, the integration of AI into blockchain data analysis has the potential to transform how we utilize the vast quantities of data produced by blockchain technologies. This integration enables more effective fraud detection, predictive analytics, and improved decision-making. As blockchain technology and AI continue to evolve, their combined use will likely become increasingly sophisticated, offering more significant insights and benefits to users and organizations. The symbiotic relationship between blockchain and AI marks a new frontier in data science, where the sum of their integration exceeds the capabilities of each technology independently. 7.8 Data Science versus Machine Learning. Data science and machine learning are interconnected fields that are often mentioned together. However, they encompass distinct concepts and methodologies. Data science is an interdisciplinary field that focuses on extracting knowledge and insights from various forms of data, using scientific methods, processes, algorithms, and systems. It involves a spectrum of techniques drawn from many areas within the broad range of mathematics, statistics, information science, and computer science, including signal processing, probability models, machine learning, statistical learning, computer programming, data engineering, pattern recognition and learning, visualization, predictive analytics, and uncertainty modeling. Machine learning, on the other hand, is a subset of artificial intelligence focused on the development of algorithms that can learn from and make predictions on data. Machine learning enables computers to handle new situations via analysis, self-training, observation, and experience. It operates on the notion that systems can identify patterns, learn from data, and make decisions with minimal human intervention. By utilizing algorithms that iteratively learn from data, machine learning allows computers to find hidden insights without being explicitly programmed where to look. The role of data science is more encompassing than that of machine learning. It involves the creation of methods for recording, storing, and analyzing data to effectively extract useful information. The scope of data science includes the planning of data collection methods, data cleansing and pre-processing, performing exploratory data analysis, and using various analytics and visualization tools. Data scientists must be proficient in using these techniques to uncover the stories told by the data and to communicate the results effectively. Machine learning experts, conversely, focus primarily on developing algorithms that can be used for prediction purposes. They are tasked with implementing these algorithms, tuning model parameters, and ensuring that models can generalize from training data to unseen data. Machine learning is one of the tools in a data scientist's arsenal, but not the only one. It provides the statistical foundation for making inferences and predictions, which are key in many complex data science problems. An important distinction between data science and machine learning is the overall goals of practitioners in each field. Data scientists aim to understand the broad trends and structures within data, investigating complex problems through a data-driven approach that may involve hypotheses formulation and testing. In contrast, machine learning engineers are more concentrated on creating and optimizing models that function within the data-driven applications which data scientists help to design and conceptualize. Furthermore, data science integrates various machine learning models with other statistical tools to create actionable strategies that can inform decision-making and strategy. It takes into consideration the data as a whole, ensuring that the data's quality and structure are suitable for analysis. Data scientists often need to communicate their findings to stakeholders who may not be well-versed in technical aspects. Therefore, they must be skilled not only in data analysis, but also in storytelling and visualization. Within a typical machine learning workflow, the focus is usually on model development, selection, evaluation, and refinement. Machine learning engineers employ numerous algorithms, from simple linear regression to complex neural networks, adjusting them to work effectively on the problem at hand. One key aspect of machine learning is the emphasis on predictive accuracy and the capability to automate decision processes by conditional probabilities, clustering and classification techniques, and nonlinear modeling. The tools and programming languages used by professionals in both fields can sometimes overlap. For instance, Python and R are popular choices for both data science and machine learning because of their powerful libraries and frameworks. Despite this, the usage of these tools often differs. Data scientists may use these languages for a broader range of tasks, including data manipulation, statistical analysis, and visualization. Machine learning engineers, in contrast, might dive deeper into the use of specific libraries like scikit-learn, TensorFlow, and PyTorch that are designed for machine learning tasks. The educational background of individuals in the two fields can also differ. Data scientists typically have a strong foundation in statistics and mathematics, as well as knowledge in the domain of application. This holistic view is crucial for framing the right questions and making sense of the data in context. Machine learning engineers, however, often stem from a computer science background, with a focus on computation and algorithmic understanding, equipping them to innovate in the development of new machine learning techniques and applications. Lastly, it's important to note that the distinction between data science and machine learning is not always clear-cut. The rapid evolution of technology and methodologies can lead to overlaps and convergence between the two. Data science projects can be heavily based on machine learning, and vice versa. Professionals in both areas continue to work together and influence each other's disciplines, leading to increasingly sophisticated and integrated approaches to data analysis and interpretation. It is crucial for individuals in these fields to maintain a dynamic learning mindset, as the landscape of data, its applications, and the tools to process it are continuously evolving. 7.9 Cloud Computing in AI. Cloud computing has rapidly become a key enabler for AI development and deployment. Leveraging the cloud for AI initiatives provides numerous benefits, including but not limited to scalability, cost efficiency, and accessibility. The cloud infrastructure allows for the storage, processing, and analysis of vast quantities of data, which is conducive for training complex AI models. As AI models often require substantial computational power, cloud services offer a pragmatic solution by allowing access to high-performance computing resources on demand without the need for significant capital investment in physical hardware. The most prominent cloud service providers, such as Amazon Web Services, AWS, Microsoft Azure, and Google Cloud, have recognized the synergies between cloud computing and AI. They offer specialized AI services and tools that are designed to lower the barriers to entry for businesses and developers who may not have the expertise or resources to build AI systems from scratch. These platforms provide pre-built machine learning models as well as development environments that support custom model building, allowing users to focus on fine-tuning models for specific tasks without worrying about underlying infrastructure. One crucial aspect of AI development within the cloud is the democratization of AI tools. By providing access to advanced machine learning models and algorithms via APIs and services, cloud providers make it feasible for a wider range of users to implement AI solutions. This broad access also spurs innovation, as more diverse minds can contribute to solving complex problems through AI. Moreover, cloud-based AI tools often come with user-friendly interfaces that enable individuals with less technical expertise to deploy machine learning models, thereby expanding the reach of AI technology. Another key component is the collaborative nature of cloud computing in AI. Teams around the world can work together seamlessly on AI projects, sharing data, models, and results securely over the cloud. Collaboration tools integrated into cloud platforms further streamline the process of development by allowing teams to track changes, manage versions, and maintain a single source of truth for their AI initiatives. This level of collaboration is not only efficient, but also necessary for tackling the vast, complex datasets that AI models frequently require. The integration of cloud computing with AI also creates opportunities for enhanced data security and privacy. Given the sensitivity of the data often processed by AI systems, cloud providers have invested heavily in securing their platforms. Rigorous security protocols, encryption, and compliance with international data protection regulations are standard offerings. AI systems benefit from these layers of security, which endeavor to protect data both at rest and in transit. Scalability is a hallmark of cloud services, and it is particularly vital for AI applications. As machine learning models grow and datasets expand, the computational requirements can change dramatically. The ability to scale resources up or down with cloud computing ensures that AI projects can adjust to fluctuating demands without service interruption or degradation of performance. Such flexibility also helps manage costs, as resources can be released when not in use, avoiding expenses associated with idle computing power. In addition to scalability, the elasticity of cloud resources simplifies the process of experimenting with different AI models and configurations. Experimentation is a cornerstone of AI development, and often multiple iterations are needed to optimize performance. Cloud services enable rapid provisioning and dismantling of environments, making it feasible to trial numerous approaches in parallel, significantly reducing the time to find the most effective solutions. Cloud platforms have also streamlined the deployment of AI models, allowing for rapid integration into existing applications and systems. This capability to deploy AI models as APIs makes it possible to bring intelligent features to market quickly and to a broader audience through the cloud. Companies can thus enhance their products with AI functionalities like chatbots, voice interfaces, and recommendation systems, creating more personalized and engaging user experiences. In terms of maintenance and updates, cloud computing streamlines these processes for AI systems. Automatic updates and patches can be applied to models and infrastructure, ensuring that the latest security measures and optimizations are in place. Continuous integration and deployment pipelines available on the cloud can automatically retrain models with new data, keeping AI solutions up to date and improving their accuracy over time. Finally, the financial aspect of leveraging cloud computing for AI cannot be overstated. The operational expense (OPEX) model of cloud services replaces the capital expense (CAPEX) model associated with buying and maintaining hardware. This shift in financial strategy means that businesses can channel funds into innovation and development rather than infrastructure. Moreover, the pay-as-you-go pricing models of cloud services provide predictable costing, which aligns well with planning and budgeting for AI projects. The integration of cloud computing with artificial intelligence is a significant development in the field of technology. It facilitates the creation, deployment, and management of AI applications, making these sophisticated technologies accessible to a larger population, fostering collaborative development efforts, and promoting innovation. The adoption of cloud computing and AI is likely to continue its upward trajectory, as it remains a critical driver for the evolution and democratization of artificial intelligence capabilities across various industries. 7.10 Real-World Data Science Projects. Data science and artificial intelligence (AI) have become integral components in the blockchain domain, enabling sophisticated analyses and intelligent decision-making processes. In fact, real-world data science projects often utilize blockchain technology to enhance security, improve audit trails, and ensure data authenticity. Blockchain's immutable ledger system allows for the creation of robust datasets that are resistant to tampering, which is especially important when working with AI models that require large amounts of reliable and accurate data to function optimally. In these kinds of projects, data scientists focus on collecting, pre-processing, and analyzing data stored on the blockchain to derive meaningful insights that can subsequently inform AI algorithms. Furthermore, the decentralized nature of blockchain plays a key role in distributing AI tasks across various nodes, thus improving model performance and scalability. One common application of data science in blockchain is fraud detection. Financial sectors particularly benefit from machine learning models that can detect unusual patterns indicative of fraudulent transactions. For such applications, the blockchain serves as an unalterable record of all transactions, thereby providing a clear trail for analysis. Data scientists can use this information to train models that not only understand typical transaction behaviors, but also recognize anomalies with high precision. By taking advantage of the blockchain's transparency, machine learning algorithms can be continually updated to reflect new forms of fraudulent activity, thus enhancing the robustness of fraud detection systems over time. Supply chain management is another area where data science projects thrive with blockchain integration. Given that supply chains often involve multiple stakeholders and plentiful data points, blockchain's ability to retain an immutable history of transactions ensures that all data relevant to the supply chain is accurate and unaltered. Data scientists can utilize this data to optimize supply chains, predicting delays, and identifying inefficiencies. Through the use of AI, for instance, predictive models can forecast demand for products, the potential impact of external factors on supply routes, and even advise on the best strategies for inventory management. The transparency and verifiability brought about by blockchain technology mean that AI models in supply chains can be trusted, and their predictions are based on sound and tamper-proof data. When it comes to healthcare, data science projects can greatly benefit from blockchain to ensure the confidentiality and integrity of patient data. Healthcare data is incredibly sensitive and requires the highest levels of security. Blockchain can be employed to create secure channels for exchanging information, with access controls managed transparently and changes to data logged indelibly. This allows data scientists and AI practitioners to safely access a patient's historical health data to build personalized healthcare models. AI can predict patient outcomes, customize treatment plans, and even help prevent disease by analyzing patterns that might not be evident to human health professionals. The pairing of data science and blockchain in healthcare addresses both the innovative potential for personalized medicine and the stringent regulatory requirements for data protection. Energy sector applications have also seen the beneficial use of data science and AI on the blockchain. For instance, smart grids employ blockchain to record transactions between energy providers and consumers. Data scientists work with these vast amounts of data to enhance energy distribution efficiency, forecast consumption patterns, and integrate renewable energy sources effectively. AI algorithms are developed to manage these smart grids autonomously, adjusting energy distribution in response to real-time consumption data, which can mitigate power outages and optimize energy usage. Blockchain's secure nature gives operators and consumers confidence that the market is fair and that records of their energy usage are accurate. In the real estate sector, blockchain combined with data science can streamline property transactions and management. A blockchain can store property records with a high degree of certainty regarding their authenticity. Here, data scientists create models that can evaluate market trends, assess property values accurately based on vast amounts of historical data, and identify investment opportunities. Using AI, these applications can predict market dynamics and offer stakeholders relevant and timely advice. The transparent and immutable recording of data ensures that all analyses are grounded in verified transactions and historical records, reducing the risk of fraud and errors that can be costly in real estate dealings. Another burgeoning area for data science and AI within blockchain is in the realm of social media and online content. Blockchain can help verify the origins and authenticity of digital content, which is particularly significant in the age of fake news and digital misinformation. Data scientists can use this information to build algorithms that identify reliable sources and flag content that appears to be false or manipulated. AI can be trained to understand the nuances of language and cross-reference claims with verified information, bolstering the capacity for accurate news dissemination and content credibility. Furthermore, in the realm of environmental sustainability, blockchain's capabilities can be harnessed to enhance tracking and reporting on environmental impacts, enabling better management of resources. The data recorded onto a blockchain about emissions, waste generation, resource usage, and conservation efforts is verifiable and can be used to make more accurate AI-driven predictions about environmental outcomes. Data scientists can analyze this data to help companies understand their environmental impact, devise strategies for reducing their carbon footprint, and comply with regulations. In this way, AI and blockchain are wielded as tools for both corporate accountability and environmental stewardship. The integration of the Internet of Things, IoT, with blockchain and data science is another novel development. IoT devices generate vast amounts of data, which when recorded on a blockchain, can be utilized by data scientists to track device performance, detect potential failures, and optimize maintenance schedules. Furthermore, AI can process this real-time data to automate decisions, such as recalibrating a device's settings in response to environmental changes. This seamless integration of blockchain, IoT, and data science paves the way for more efficient and reliable systems across industries ranging from manufacturing to home automation. Finally, the entertainment industry has also begun to utilize blockchain to manage digital rights and royalties transparently. Data scientists employ blockchain data to develop systems that can automatically track content consumption and ensure that creators are fairly compensated. AI can be deployed to analyze consumer behavior and tailor content recommendations to individual preferences, thereby enhancing user engagement. Leveraging blockchain's data integrity and AI's analytical prowess ensures that payment systems are just and content recommendations are pertinent, benefiting both creators and consumers within the digital media space. Through these real-world applications of data science and AI in conjunction with blockchain technology, it is clear that an interdisciplinary approach can lead to revolutionary changes across various sectors. Each implementation underlines the importance of having a structured, secure, and reliable source of data, a bedrock upon which data scientists and AI algorithms can operate with confidence. As blockchain continues to evolve, data science will undoubtedly play a pivotal role in finding new and impactful ways to apply this technology for the betterment of industries and society at large.